This talk is all about what electricity can do to your body, the rules and regulations in Queensland, who is an authorised person according to the Electricity Act of Queensland, the standards that are applicable, some of the protective systems that can help you stop being injured by electricity, by coming in contact with power. Electricity supply arrangements in southeast Queensland, so you're sort of familiar with some of the what's around on the poles and underground. LV versus HV in terms of injuries. And what precautions, and probably the most important thing I wanted to talk about, was what precautions should us amateurs be taking when working with dangerous voltages. And a few little tips and tricks about using mains in your projects. Because I presume everybody here is doing something on their workbench, as you should. So just a few things which are law and also just plain common sense. Right, so I apologise to those people who know all this material in advance. This is a bit of a recap. And if I've made a mistake, please pull me up. I don't pretend to know everything about everything, anything. Okay, so for those who don't know me, there's my brag. I'm a licensed electrician. I've got an associate diploma, a bachelor degree, masters. I'm a senior member of the IEEE, a big standards organisation for electrical engineering. I'm an RPEQ, so I'm registered as a professional engineer in Queensland. My union is Professionals Australia, John, there you go. So I'm a registered professional engineer. That was the pathway toward RPEQ. And I'm currently working at Energy Queensland. And Energy Queensland, for those who don't know, own two small little companies called Ergon and Energex, plus Eureka is another. I'm working in that company, standardising the deployment of SCADA or control system devices for every control system in Queensland, including isolated systems and customer connections. So I'm doing some very interesting work with big solar farms and big batteries at the moment. Amateur radio wise, I was first licensed in 2000, VK4 TGV. That's because I like the trains in France. So I don't know if everyone's been to France and been on a TGV, it's pretty amazing. I held 9V1PS while I was based in Singapore. I was based in Singapore for about 4 or 5 years. I'm now VK4EA and KQ4PS, so I have an extra licence in the USA as well. I'm an AMC assessor and a volunteer examiner for the ARRL. My current interests in radio are ATV, APRS, microwaves, portable gear for all those bands, which you guys are probably not the slightest interested in except for Gary. And what else? Oh, I'm currently working on my microwave home station and 10 gig EME. So that's taken a bit of a back seat because of other commitments at the moment. But anyway, getting there. All right, so I talked about that. So firstly, how do you identify a dangerous situation? So you're approaching something, you're doing something in your bench, you're out at someone's friend's place, they're showing you a bit of gear. I would say that any exposed conductors I would treat as life-threatening. I even am cautious around 12 volts, touching exposed metal surfaces. That's just me personally, because I'm a bit risk adverse. I've been hooked up a couple of times, it's not fun. If you hear any crackling, that's pretty much a dead giveaway. And you can sometimes hear that in really, really wet weather around substations. You can hear the corona discharge. Very, very distinctive sound to my ear. Of course, smoke, smell, visible arcing. But arcing is noisy by its nature. So if you see arcing, don't go near it. And fire, of course. That's just common sense, I hope. All right, so in southeast Queensland, we've got a couple of different ways of getting power from the power station to your home or to your business. The low voltage, which is should be 230 volts AC, which is a new standard now, or 415 line face-to-face, is 4 wires. So you've got 3 phases and a neutral. So that's the bottom rung of the overhead lines in your street if you've got overhead power. That's the 4 wires. That's LV, what I call LV. Actually, what I call LV now is 11 kV. I've changed a bit. If you see the 3 wires above it, that's now HV, or medium voltage. So it could be either 11 or 33 kV, and it's 3 conductors because there's no neutral. The really big 3-wire feeders you see could be 110, 132 kV face-to-face. And the big kahunas, like the ones out at Murrumbong, those towers running through that property, that's Powerlink. That's a transmission authority. That's 275 kV line to line. Other distribution voltages in regional Queensland, which we don't see in southeast Queensland, are 22 and 66 kV, because it's a shitload cheaper, and there's not much load on some of those feeders. In other parts of the country, you'll see 220, 330 and 500 kV as well. So Victoria has a complete 500 kV transmission system. It's quite unnerving to go into one of their terminal stations when it's raining, which it always rains in freaking Victoria. Every time I've been to a bloody terminal station in Victoria, I feel the electric field in my arms through the PPE, and you can hear the capacitive hats snap and crackle. So it makes me very nervous. All right, so, and I hope this is obvious, any contact with those energised feeders at those voltages, and you've got a path to ground, is lethal. All right, so don't go near them. The higher the voltage will govern how fast you become a crispy critter. And I mean that every literal sense of the word. You will not survive. You will be ash. So I'm trying to scare you, I hope I didn't. So overhead protection systems, so obviously you can't have all that power, all that massive fault current without some sort of protective systems. Firstly, it protects the plant, because the plant is very expensive. That there pictured is a 11 kV circuit breaker. Now that stands about that high, and that arc flash chute goes back probably about 1.5 meters to 2 metres. That's $30,000, that thing. So that's designed to trip at 1200 amps at 11 kV. Imagine how much power, if you do the quick little sums, 11,000 times 1200 amps times 3, that's a lot of power. That's a lot of amps, a lot of watts. So the fault current that those things can provide is quite amazing. So at the top of that thing is what's called a protection relay. That relay will be looking at the currents flowing and sampling those currents very quickly to work out if there's a fault situation. So that's what's protecting your house. That's what's protecting the cables running down the street, is that big kahuna. So they're in every substation in the world. Maybe not a particular one. That happens to be a Genie Evo made by Schneider. We just changed to a Malaysian one called Tamco. For your street feeders, you're relying on big cartridge. I couldn't find one, but it's about the size of that head of that hammer. But there's 800 amps on every pole-top transformer per phase. So you can imagine to draw 800 amps at 240 volts, that's a fair bit of current, fair bit of fault current. So your house might not trip that. I doubt it very much it'll trip that. Right, so the reason I'm saying that is if you come across a wire on the ground, that's all there is between you and death. And that's not going to save you. The other thing that these relays do is that it can detect an earth leakage. So they call that sensitive earth fault or earth fault. The relays are set up to detect several amps of earth current. So there's very clever mathematics in these things that can work out, okay, there is a path to ground, and it just assumes, okay, there's a wire on the ground, there's a small amount of leakage current travelling from where the wire's in the ground through the earth mass back to the substation. So you're pretty much okay if you fall on a wire just after it's fallen down. But I wouldn't recommend doing it if you can avoid it. So yeah, like everything with electrical stuff, and EFMs are always taught, assume everything is live. Blanket just assumption, it's all live until you can prove otherwise. And I wouldn't recommend putting a multimeter on 11 kV cable. That will not end well for you. So wait for Energex to come before you get near it. Underground, if you're digging and you encounter that yellow tape, please stop. Stop immediately. All right, I've got a little video here, and I know John probably is well aware of when you go on an excavator that if you see one of those things, your hands off the controls and run away, because if you go any further, so let's see if this works.
Is thought to double for every 6 to 8 degree rise in operating temperature. So when we test oil samples, we look at the levels of carbon monoxide, carbon dioxide dissolved in the oil. You don't want to see, if you see, for instance, carbon monoxide.
So now that's an arc that's been self-sustained by the H by 11 kV. It'll keep going until the protection system operates. If I see that, you don't see them now, I've run. Watch how these guys respond when it gets hit. I'd do that too. There is plenty of stuff on YouTube about how, that's just exposed cable arcing. So that's not LV, that's 11 or 22 kV. And if the protection system in the substation has been set up properly, it'll do that all day. Right, so suffice to say, if you see that, don't go near it. Because what can happen with some of these joints is they can explode if they're not done properly, or they get hot. So we've had a couple of situations in southeast Queensland where people have been walking along the footpath and there has been a joint blow up, and it's lifted those big concrete, the big concrete pit covers. They're probably about 60 kilos each or something. There's a 2-person lift. They've risen that high off the ground. So that's the amount of electrical force behind these things. Right, so that's enough of that shenanigans. Yeah, so what's happened there is you're getting a face-to-face fault. So that could be at 11 kV, 22 kV, 33 kV. Hopefully at that stage the relay in the substation's gone, well, that's a face-to-face fault, I'll trip. But as you saw there, it'll keep going, it'll just keep going with the arc because hasn't hit the overcurrent setting in the relay. So in that case, stay clear. Right, so clearance distances, this is interesting. For me, being an electrical worker, I can touch 240 volts with a glove. I'm allowed to do that. I wouldn't do it without a glove. That would be silly. For 11 kV, the closest you probably should be getting to 11 kV is 1.5 metres, and 33 kV is 4 metres. Now, any closer than that, you've got a risk of an arc, of something coming out of the wire at you if you've got an earth potential. So if you're standing barefoot in the ground in mud or something like that, and you get within a few metres of 33 kV, you can expect to feel something. Briefly. Probably the last thing you think. Okay, so going back to 230 volts, 410 volts is what we would normally experience in our households and doing projects that are powered from mains. The injuries you get from LV, this is just a recap, basically the foundation licence. If it's hot, you're going to get burnt from high currents. If it's high voltage, you're going to get electrocuted. The human heart only needs 15 milliamps to stop pumping properly and to go into fibrillation. Yeah, so if you hold on to an active conductor and touch your sink or something like that has an earth, you've got some current flowing across your chest. You'll feel your muscles spasming at 50 hertz, and your heart will not like it and it'll probably go into fibrillation. Then you need an AED or you need a paramedic ASAP. So what's the best way to avoid injury? Well, what do you think? Turn it off. Is the safest thing. Turn it off, unplug it. Yeah, or disconnect, and don't touch, and you're absolutely certain it's dead. So all electricians will carry the little buzzer pen with the light indicator. You'll see them rubbing it up and down their sleeve to get some static electricity to make sure it works okay. In the old days, you would test that with a live circuit first before you test for dead, because you never know whether the element inside is or your battery's dead. There's been a couple of apprentices die because they let the battery in their live line indicator go flat. So always check your device. Make sure your multimeter is not configured to measure current, because you'll get a nasty surprise. Right, so putting dead short across active and neutral, it'll be exciting. I'm sure that's all common sense. Yeah, people? Please tell me it's common sense. Right, so you'd think that 240 volts would be safer than 11 kV. Right, so what these guys are doing is they're type testing a switchboard. So they're purposely introducing a fault. So they'll wrap fuse wire around the bus bars to make the arc start and to see how the board reacts. Right, and I don't think this went well. So I've been to the testing facility that Energy Australia have down in North Ryde, where they test this sort of stuff. It's a really magnificent, I think it's been shut down unfortunately. That's 415 volts. Right, so that person or that mannequin got blown backwards. And most likely you'll be severely burnt, as well as being deaf. Yep. Now obviously there's a fair bit of energy behind that that's connected to a transformer. You probably won't have the same fault current at your house, but I'll still treat LV with some respect. I've seen pictures of people disconnecting meters, like household meters. This again in the USA, we've got plug-in meters where we don't really have them here. And they plug them in the wrong way and they've been thrown backwards. So be careful. There's another arc flash video here. Oops. So this is again probably more of a commercial type switchboard, and this guy rabbits on for a bit, so I'll just skip ahead because he's a yank. So he's going to hit the go button shortly. So again, they've wrapped fuse wire around the active conductors and they've energised the board. That's a fairly typical board you'll find in most commercial premises. Even if you've got 3-phase in your house, you've probably got a board like that. Can you see that arc jumping out? Scary stuff. That's 415 volts. Right. Hot, yeah, hot and loud. Okay, so legislation, the boring stuff, the laws. There's Electricity Act of Queensland. There's national electricity rules. There's a number of standards that we must apply, that we must conform to. So the Electricity Act says you must follow AS 3000, which is Australian standard number 3000, and there's the latest version, I think, is 2021. So they're the wiring rules. They're known as the wiring rules. You must follow them. Then associated with them is AS 3008, which is a selection guide for the cable sizes. So, you know, electrician engineer must choose the right cable sizes, particularly to carry the right fault current. And there's AS 3107, which I haven't gotten there with for the testing. So doing your fault loop impedance, your RCD tripping time, your earth conductor integrity, plus your polarity. Now, because it's AC, don't think polarity is not important. It is very important for protection systems to work. So Electrical Safety Office, they're the enforcers. It's not Energex or Ergon, it's the ESO, Electrical Safety Office. So if somebody has an accident or there's some rule issues with the wiring installation, the ESO will investigate. They may call on the utility to go and disconnect, but it's mainly up to the electrician to do that work. So distribution utilities, like the one I work for, Energy Queensland, Energex Ergon, we need to comply to AS 3000 like everybody else. So we don't get an exemption. However, we do have the power to Form 3 I think it is, as in that if I see a dodgy installation, I can go and disconnect it as an electricity officer. I have that power. And as an electrician, we're supposed to report that stuff to the ESO as well. So I don't work as an electrician, so I don't see it all day, every day. But we certainly see some dodgy stuff that people try to connect to the network. And that may seem a little overreach and a bit like lack of freedom and stuff like that, but it is for your safety and for the rest of the people around your safety. I hope that's just common sense. Okay, and so the Act talks about who an authorised person is. So they talk about 4 roles. So one is an engineer. Now, being an engineer, you can carry out electrical work that is part of your calling. So me as an electrical engineer, I can probably go and use a multimeter to go and measure a few things. But I can't change power points or wire up a house. That's not part of what my calling is. So if an engineer tells you I can wire your house, ask to see the electrical work licence. Then there's the electrical worker or electrical fitter mechanic. I've got one of those licences as well. An EFM ticket only allows you to do work on your own premises or for family. Okay, you can't do paid work, you can't charge people for electrical work or do work outside of your own premises. So the extension to the electrical worker, a licensed electrical fitter mechanic needs to have a contractor's licence, a Queensland contractor's licence. Right, and that includes a very important component, that's insurance. So public liability and professional indemnity insurance. So if you do something wrong, you're not going to lose your house or go to jail, hopefully. Apprentices, they must be supervised. They're still considered an electrical worker, but they cannot work unsupervised. So an EFM must supervise them, and they can't supervise them from down the street. They've got to be there, pretty much looking over their shoulder. And then in Queensland we have these restricted tickets which allows tradesmen like plumbers and aircon mechanics to disconnect and reconnect the devices they're doing. So a plumber could replace a hot water system and disconnect it, replace the hot water system and reconnect it to the existing wiring. A restricted worker is not allowed to install new cables, new points, new isolators. You have to be an electrical fitter mechanic to do that. So there are only 4 people that are authorised to work in the power industry. So what happens if you're not? Well, there's a series of penalty units depending on the type of offence. If somebody gets killed by work that you've done, if you've been unlicensed, when a electrical contractor has done some work and somebody is injured or killed due to their work, it would be at least a loss of licence, at least. If you're unlicensed, and your house burns down and your insurance company figures out you don't have a licence, you've got no insurance. Right, so that's a really important thing to consider. If you're not licensed and your wiring kills somebody, expect an orifice to be enlarged in the big house for quite some time. You will go away, you'll go to jail. Am I scared you enough? Or you're bored? All right, so there are things in there that are there for protection, okay? So the first thing is the earth, is the ground mass. So the ground mass is designed to take power away from you in the event of a fault. Right. So the rule is with any appliance, with any bit of the plant, any exposed metal conductor surfaces should be earthed. Okay. Then there's the overcurrent. So if you here's an overcurrent device. So it's a 6 amp miniature circuit breaker. That's an overcurrent device. So like a fuse, it'll carry 6 amps forever. As soon as you get to about 7 amps, it'll trip. If you put 20 amps on it, it'll trip very, very quickly, depending on what curve it is. So I think that's an A curve. No, it's a B curve. And fuses, I've talked about fuses before. There's basically 2 types of fuses. One that the glass-filled ones or the plastic ones, so you can see the conductor. They're generally not used in the utility industry. They're the ones we use in there are called HRC or high rupturing capacity. So again, big things like that, they're in a ceramic enclosure and they're filled with sand. The whole idea of that is that when you do get an overcurrent and the element burns or clears, the sand then quenches the arc. And they're also quite a bit stronger too, because fuses will blow up, they will explode if you put too much fault current on them. We don't really want that happening, so they fill them with sand, make them strong so they can cope with the fault. And the one that's just probably most important, well, it's not the cure-all, but it is important, is the RCD, residual current device, or your earth leakage circuit breaker. That's a 4-pole variety. Very popular at the moment because it's cheaper to put those in than to put the individual RCDs in. So it's a single pole RCD, so it's built in with a circuit breaker as well, whereas that is just purely RCD and it can protect up to 3 circuits. So that's useful for if your board doesn't have a lot of room, you can use that to put RCD on your house. But if something does trip and you're not in your house, your fridge is going to go off and you're going to come home to a stinky house. So I always thought these things are a good idea because if something trips off one circuit, your fridge has got a good chance of keep going. So these things rely on the switchboard being wired correctly, and that's the main thing is that you got the polarity right, so your active and your neutral are the right way around, and there's a MEN link between the neutral and the earth bar. So there should be only one of those per earth stake. So that then allows the RCD device to operate. I've got another slide which shows you how they operate. I'm pretty sure you all do, but I'll take you through it. The other thing to consider with an RCD is that if you grab an active conductor there and grab a neutral conductor there, what's going to happen?
Just another line on the circuit.
The RCD will not operate unless it has a path to ground. All right, so it's not the cure-all, it's not the be-all and end-all of protected devices, but it's pretty good. All right, so don't assume because you've got an earth leakage device in your supply that you're completely protected. You're not. So the RCDs, they rely on a small difference between the active and neutral conductors, so they're sometimes known as core balance, or in the United States they're called ground fault interrupters. So earth leakage circuit breaker, ground fault interrupter, residual current device, earth leakage, all the same thing, same principle. So there's a little diagram showing you the circuit of what an RCD does. So the idea is that if you touch, say, the active conductor like that, there's now a path through my arm to that conductor. And then that means there's a difference in current between this toroid. So that means it'll generate a small current and operate the relay, or trip it. But it relies on a good ground system and your neutral being in the right spot. So without your neutral being connected, you've got a dodgy neutral, these won't work very well. So that's a real problem in some of these older dwellings where you've got a dodgy neutral, particularly in Sydney where these old terrace houses, they relied on the lead pipes sometimes for the return current. And you can pick that up in the distribution system. We've done a lot of work in Queensland with that to pick up dodgy neutrals. But the main problem is the electrician has swapped your active and neutral around. You're in real trouble if that happens. Right. I've seen it a couple of times in people's houses where they wired up a power point and they don't know what a red and the black wire, it's just AC. What's the difference? There's a massive difference. See other parts of that circuit too is a test button. So that's normally there's a test button there. So a test button, you should be pressing that at least every 12 months, at least in your house. Here the rules are we've got to keep a book. I haven't done that yet, I should do that, is test the RCDs and keep a book of the times and the level that they tripped at. So most of these, the RCDs in your house are configured to trip at 30 milliamps of leakage current. In medical situations, that you see the red ones on the wall in wards and hospitals and surgeries, they trip at 10 milliamps. So the idea of that is that you're minimising potential injury from getting exposed to a dodgy appliance or dodgy wiring. So I can't emphasise enough how important it is to make sure your house, you can't sell a house now or rent a house now without having RCDs in all your circuits. In the old days you didn't have to have an RCD on your oven and your cooktop, that's changing. You've got to have an RCD on your lighting circuit now and every power circuit. Okay, so if you buy, I'm sure if people have bought a house or built a house lately, you would have seen all those RCDs everywhere. That's the law now. But again, not the be all and end all. So I want to quickly touch on AC versus DC. So the rules in Queensland are that if the DC voltage is over 100 volts and the AC voltage is over 50 volts, you have to be an electrical worker, a registered electrical worker. But I think DC is arguably a little more dangerous than AC. And the reason for that is that all these AC rated devices rely on the zero crossing of the voltage. So AC obviously, sine wave, don't tell you that. If there's a fault and the voltage, there's a fault, the fault will keep going as the voltage rises and comes down, but as it gets to zero, the 0 point, there's no volts, then there's no potential, the arc will clear. But if you've got 300 volts from, say, a solar PV system, it won't stop. So there's no zero cross to extinguish the arc, so it'll keep going. It's been a real problem with some of these solar PV systems in the past where they've used dodgy Chinese isolators, which are not rated, or using AC rated breakers in your DC circuits. Not a big problem at 12, 24 volts, but certainly once you get up to where the solar PV systems are 100 to 300 volts, you've got to use DC rated equipment. There's no choice. The other thing is, I talked about the transpose active and neutral. That's a polarity check. So when you get your distribution utility or your contractor to come and hook up the power to your house, they have to do a polarity test to make sure the active and neutral aren't swapped. So you really need that neutral to be right in the right spot for your earth leakage to work. It's also relying on, in an overhead area, every fifth pole you'll see a down lead coming down. That's connected to the neutral wire on the overhead. So it's relying on that wire, that conductor in the ground, for the return current to go back. Right? So without that and an earth stake in your house, there's some serious issues. Now what's happening at the moment is these, I can't say, can I? Too late. These fuckers will go along the street with an axe and reach up as high as they can, chop that conductor off, at the ground chopped off, take it off to the recycler and get money for it. So if you see that, call Energex, because that's a dangerous situation. Those down leads are there for a very, very good reason. I kind of like to think if they go into a substation and try and do that, the problem's finished because they'll disappear into a puff of smoke. And it happens a lot overseas. Copper theft is a real problem. And so that leads into the dodgy neutral. So the dodgy neutral, if it's not connected properly, you've got a bad connection, your protective systems are not going to work as well. You'll start to get things like tingly taps and tingly showers and stuff like that. If that's the case, call it Sparky straight away. Don't hesitate. Just pay for it to get fixed. It's not worth your life. And a missing earth, well, that RCD will have trouble working without sort of some decent path to ground back to the earth stake, to your MEN system. So having an earth conductor is really important. So anything metal attached to the ground will get tingly with this sort of situation, with either a dodgy neutral as the most likely cause. And that can also happen outside the house as well, unfortunately. So it may not be your installation in your house, but the first protocol is always call your electrician to get it tested. Call your Sparky. If you can avoid touching it, turn your power off if you can. Is always my advice. If you can, turn it off. Does everyone know where their main switch is in their house? It's a good thing to know. So an EFM or a licensed person shouldn't make these mistakes. But I can't say it doesn't happen. So AS 3000 and AS 3108, 3807, I can't remember, the testing standard has some clear testing requirements to identify these things. So a licensed Sparky will have a loop fault impedance tester, and will have an RCD tester. They will have all the means to isolate where the problem is. If they don't, get another one. Another thing that I think we come across quite regularly when we go portable is portable generators, and it's always been a bit of a bugbear for me when it says, oh, we should put an earth stake in that thing. You never, ever, ever earth a portable generator, because the active and neutral, the neutral is not connected to the case. So the neutral pin, the right-hand pin in the three-pin connector, it's never connected to the earth because it can float up and down. I love this quote: an earth stake and a portable generator will stop it rolling down the hill. It won't protect you, all right, without the proper protection systems. To do it properly, you need to have a switchboard and an earth stake separate to the generator. That's the right way to do it. But with my little Honda 1 kVA generator, I never worry about it because I always use proper leads and don't let it get covered in water and stuff like that. Having said that, for semi-permanent and permanent genset installs, you can, that's quite okay to put them in, but the law and the rules say you've got to switch to neutral at the same time when you change over switch. Okay, you can't leave the neutral connected. Okay, that's not a good practice. So that changeover switch over there switches both the active and neutral. That's the rules. And I'm sure I don't have to say the double male plug leads. I hope nobody's got one of them anymore. You do, don't you, John? So the old days, you used to get your portable generator out and plug it into an outlet in your house, plug it in, and hopefully you remember to flip the main switch on your house, and you feed your house from that generator. They're the most dangerous things you can possibly imagine ever happening. So it's just worth running an extension lead to your house rather than doing that and backfeeding it. The risk is if you leave the main switch on, you're going to backfeed the LV network into the street, and you're going to give power to the rest of your neighbours. I'm pretty certain your generator is going to have a lot of problems supplying all the houses, so it's probably going to fail anyway. But bear in mind the poor Energex worker out there working on the LV, expecting it to be dead, and you've just livened it up. So caravan's interesting because if they're off the grid, it probably doesn't matter if you swap the active and neutral on a generator because there's no tie to earth. No. But I've seen my brother-in-law had a lead that was made by his father with the active and neutral swapped, and he plugged it into caravan parks. And that was, I freaked when I saw it. I cut the plug off straight away. What are you doing that for? And I said, I don't know who wired that up, but they fucked up badly. And that's a real dangerous situation. Right? Not so bad with a portable generator away from the mains, but if you plug it into the mains, that's really, really dodgy. And I must say that the wiring rules for caravans do differ from houses. There are some differences where every caravan, every 240 volt outlet has to be a double pole. So you're switching on your power points in the houses, you're only switching your active, but in caravans it should be active and neutral. Just for those situations, in case you've got a generator where the neutral wire from the inlet is connected to the active wire, that means all your neutral pins in your caravan are live. Not good. Okay, so Homebrew. So this is probably the thing that's most typical to us as we're building our projects. Earth everything that's conductive. So this is my 23 centimetre ramp, which is just about finished. I've got the earth conductor running to the earth of the switch remote power supply, and it's also going to the chassis. Okay, and there's no plastic fasteners. It's a metal fastener, a metal crimp. Right, so it's because it's a metal case. I don't recommend you build double insulated appliances. You don't have the skills for that. You don't have the plastic moulding skills and machines to do that. So everything must be earthed. There's a fuse, and that fuse is on the line side of the switch. Right, so you at least fuse the active. I've got a bit of, I didn't bring it, I should have brought it. I've got a rotator controller at home which fuses the neutral. And that was obviously built in Japan many, many years ago, and that's a different type of wiring rules. I'm going to change it to have a fuse on the active. So what I've done here is I've attempted to keep the mains wiring. I didn't have room to sneak it. I normally sneak it around the side, but I was running out of room. So I've covered the 240 volt cabling in spiral wrap. So that effectively double insulates. There's two layers of insulation there, so there's any rubbing, it's going to go to the chassis, and as soon as any voltage appears in the chassis, the RCD should operate. I've heat shrunk everything to an nth degree, so there's no exposed live parts. So there's heat shrink on the fuse holder. There's no, so you can't come in contact, and there's heat shrink on the back of the switch. And the 240 little LED indicator I put in there, it's all insulated anyway, so it's all good. So that's your basic requirement for doing a 240 volt Homebrew project. And if you're not confident in doing it, bring it here, we'll check it. That's the advice I give you. And I'm sure people have done all this stuff for years and stuff like that, but there's a minimum standard you must follow for this stuff, otherwise you could hurt somebody. As I've shown you, LV's to be respected. I think that's it.